Welcome to Ask and Learn.
Okay, so in this problem, we're considering a situation where you have a bathtub that's cooling down and you want to warm it up by boiling water and pouring it into it. So I've done this before. It kind of works. And you want to consider things like, is the entropy changing? Is this reversible? And what is the difference in temperature, the final of the hot tub? Like, did you really warm it up? And so I went ahead and just wrote down the constants that are relevant ahead of time. Mass of the boiling water, I labeled it mass boils, 5 kilograms. The mass of the water in the tub is 195 kilograms. Initial temperature of the tub, 30 degrees C, but boom, I initially put it into kelvins because I don't want to get tripped up. And the initial temperature of the boiling water is 100 degrees C because that's the boiling point of water. Finally, the heat capacity of water, we'll need that. So I went ahead and wrote that down as well. So I'm actually going to not do the part A first. I'm just going to start with B and C, and then I'll kind of comment on A. So B, it asks for the final temperature. So with this one, you want to start with the principle that delta Q is equal to 0. So no heat enters or leaves the system. So the heat flow, but we know that the heat flow from the boiling water to the tub water, you can kind of describe the heat flowing from each system, even though they're both water. So like we can use our familiar formula, M boil, C water. And then delta T, so T final minus T initial boil. Oops, I did those indices opposite the way I did them before, but hopefully it's not too confusing. Plus M tub, C water, T final minus T initial tub. And oh look, the C of the water cancels. Oh, I'm gonna set that equal to 0. Oops. Okay. Yes. Then now you can see that the C of the waters cancel. If you take this and like algebraically manipulate it, then you'll get just T final equals mass of tub times T initial tub. Sorry, that doesn't look pretty. T initial tub plus M boil times T initial boil divided by the sum of the mass of the tub. Not the mass of the tub, the mass of the water in the tub plus the mass of the boiling water. And if you stick that into a calculator and like stick in all these constants I have written here, then maybe you'll get the same thing I did, which is 31.75 degrees Celsius. So whatever you get, you have to subtract the 273. So I guess I'll go ahead and put that minus 273. But I guess I could have just left it in Kelvin, but oh well. So that's the first part. And so it didn't really warm up the tub that much, but because it was started at 30. But, I don't know, maybe that's good enough. Okay, so now what we want to do is get the change in entropy of the system. So you're going to have the change in entropy of the boiling water plus the change in entropy of the tub water. So boiling water is going to cool, so it's going to lose entropy, but the tub is going to gain entropy because it's heating up. And then we can use the formulas that we have. So M boil, C boil. So this is for, I guess, just generally a formula for the change in entropy of a substance. It's just like heating up. So it's let's see, MC ln of T final over T initial boil. I'm just gonna double check. Yeah, no, that's right. Okay. Plus M tub C tub times the natural log of T final, which is what we solved for in the last problem, in case it's not clear. And then that's Ti tub. Okay, so yeah, if you kind of stick in all the constants from part 1, so M boils like 5, M tub's 100. Oh, I wrote C boil and C tub, but I suppose those should just be C water. Glad I double checked in case that were to cause any confusion. Well, there is a slight temperature dependence on heat capacity, but yeah, it's probably best to just a good enough approximation to treat them as the same. Okay, so if you take this and plug it into a calculator, maybe you'll get what I got, and that is 472 joules per Kelvin. Okay, so back to the idea, is this process reversible? Well, we can see mathematically it's not reversible because the entropy increases. But yeah, I kind of am struggling with come up with a good physical explanation for why it's not reversible. I suppose if you wanted to reverse it, what you would do is you could like take off 5 kilograms and you would like you have to heat it back up to 100 degrees Celsius, and then you and then that would require some type of machine that would kind of have an input and output heat. So you're going to create heat, extra heat, if you're going to boil this water back up, and then you're going to have to use some kind of refrigerator to cool the water back down to the appropriate temperature. And so yeah, hopefully that's a good enough physical explanation. It's not reversible though.